Okay, today we're going to start chapter 11, and we're only going to do 3 sections from chapter 11. And 11.1 is called Space Figures and Cross Sections, and we're going to have a quiz after 11.3. Again, you might want to pause this video at one point on this first slide so that you can copy over all these definitions. I'm just going to read them to you quickly. Okay, so the term base or base faces. They're the two congruent parallel sides of a prism or a cylinder. So again, you can see in the picture over on the right, and I'll highlight in purple, you have the base on the bottom and the base on the top. Okay, those two sides of that figure never touch. They would be parallel to each other, and they're also congruent. Okay, the edge is the segment that is formed by the intersection of two faces of the solid. So again, there's a bunch of different edges in here. Again, I'll just highlight the one that is already pointed out in the picture. That's that edge right there. Okay, but again, there's other edges. I'll do one more. I'll do this one right here. There's another edge. So any point where two sides meet is an edge. A vertex, just like with a vertex of an angle, is a point where two or more edges of the solid intersect. So again, I just highlighted two edges in red above. So that point right there where those two edges intersect is a vertex point. Lateral face, the face in the geometric solid that are not the bases. So again, if I highlight any of the big rectangles that make up the sides that would go all around, perpendicular to the two bases, those are all lateral faces. Okay, so everything from this red line up all goes with that one diagram. Okay, next, a slice. A slice is a general intersection of a plane or a solid. So think about literally taking a knife and cutting an object. A cross section. A cross section is the intersection a solid and a plane make, or a slice of the solid. So again, think about cutting a figure with a knife. A right cylinder. A right cylinder is a general cylinder whose lateral edges are perpendicular to the circular base. Okay, a right cylinder is like a soup can. A right prism. A right prism is a general cylinder whose lateral edges are perpendicular to a polygonal base. Okay, and again, you can see two examples on the right. A right prism, you can have any sort of figure be its base. Okay, again, I'm highlighting the two bases here. This has 1, 2, 3, 4, 5, 6. So that's a hexagonal right prism. Okay, again, in the other figure, you have this base and that base there, which looks like a trapezoid. So that could be a trapezoid right prism. Okay, so you can have a figure 7 sides, 8 sides. You can have any sort of figure be the base of that figure. An oblique prism is like the Leaning Tower of Pisa. It's a general cylinder whose lateral edges are not perpendicular to a polygonal base. An oblique cylinder is a general cylinder whose lateral edges are not perpendicular to a circular base. So again, prism, cylinder. This one has to have the circle. The prism can be any shape on the bottom. A general cone. A general cone is a solid figure with a curved or semicircular base with a vertex. A pyramid is a general cone with a polygonal base. A sphere is a solid three-dimensional figure that is perfectly round. It's a tennis ball, it's a volleyball, it's a basketball. A net drawing. A net drawing is a two-dimensional diagram that you can fold to form a three-dimensional figure. So think about if you cut along the outside of all of these pieces right there and then fold here, 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 and here, what it would form. You can do that with anything, not the one that I just drew there, but you can always trace that outside and think about folding it along those edges. Okay, so on the top here, again, we have a triangular pyramid on the top, and look at its cross section. If you took a knife and sliced it straight through, the cross section here would end up being a rectangle. Okay, if you took your cylinder, and again, a cylinder is your soup can, and you took a knife and you sliced it right through, the cross section that you would get would be circular. Okay, and again, if you take a this figure right here, which has a triangular base, and you took a cross section of that highlighted pinkish reddish piece right there is a triangle. So that cross section would be a triangle. And for a rectangular prism, you have, again, if you think about taking a knife and cutting it straight through, that cross section there would be a rectangle. Okay, if you take a cone and you slice it, again, if you look right here, that's going to be a circular cross section, just like the one right above it. Okay, so which figure has the same cross section as a sphere? So again, we didn't do a sphere on the top. Sorry, I was going back to C. If you took a basketball and you cut it in half, and then you were able to look at what was left, or the cut side that you cut, it would end up being a circle. So they're asking you here for which figure would also have a circular cross section. Okay, and that answer is above. The one that's going to have the circular cross section is your cone. Okay, this one would have a rectangle, number one, with rectangular prism, that would have a rectangular cross section. Okay, if you cut this one here, it would be, maybe it looks like that's a square on the bottom. Could be a rectangular also. Okay, and the other one too, again, if you cut it down the middle somehow, you're going to end up with a figure that looks like its base, which in this case looks like it's going to be a trapezoid. Okay, 3 is not the answer. 2 is the answer there. Okay. For number 2, is this a right cylinder? Explain why or why not. Okay, sort of looks like it could be at first, but again, if you go back to the definition, remember that the two bases need to be parallel to each other. So since this base is not parallel to this base, it is not a right cylinder. Okay, so no, because the bases are not parallel. Okay, a two-dimensional cross-section is taken of a three-dimensional object. If the cross-section is a triangle, what cannot be the three-dimensional object? And again, I apologize because I converted a Smart Notebook lesson to a PDF, so the answers are kind of sort of staring at you right now. So for number 1, let's talk about the cone, which is over here in green that I just put the red asterisk next to. Okay, so if you were to take the cross-section of that, again, you can see this piece of paper, which is acting as the knife is cutting it, and then the gray part that they have highlighted in here is the cross-section, and that cross-section is a triangle. Hey, it's asking you again, which one would not be a triangle? So it is not that one. Okay, for a cylinder, again, if you took a cylinder, which there is no picture here, but if you took a cylinder and again you cut it, if I scroll back real quick, because we did that, when you take a cylinder and you cut it, you are going to get a circular cross section. So at that point, that's going to be our answer. Our pyramid, again, is this one over on the right that I just put that second asterisk next to. And again, this rectangular flat piece is like their knife that they're using to cut it. And that green triangle, which I'm now re-highlighting in red, becomes that cross section. And again, that's going to be a triangle. And then for your rectangular prism, what they did was they cut it almost on a diagonal. So they cut off like the edge of that rectangular prism, and you can see the cross section there is also a triangle. So 2 is your answer there. Okay, what would it look like if we pivoted the rectangle around the given axis? So think about a piece of paper attached to a pen, and that you're just going to spin that piece of paper around. What would it look like? It would end up looking like a cylinder. Sometimes the hardest part about this section is visualizing what's going on. That's the hardest thing because we're using a two-dimensional space. Again, your computer screen, is it your phone, wherever it is that you're watching this is two-dimensional, and we're using it to describe something that's 3D. So that's always a challenge. Okay, for 5, we're given the three-dimensional figures. Let's talk about what similarities do the cross sections have and what differences do the cross sections have. So again, we're going to imagine just taking a knife and just keep making slices through that figure. And what would be happening as you're taking those slices? Again, parallel to the base. Again, very hard to conceptualize this when you're using a 2D space. So same thing here. We're just going to take slices of this and go up and up and up and up. Okay, so let's talk about what the similarities are first. If you take the cross section parallel to the base, and both cross sections are going to have the same exact shape. It's going to be the shape of 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So both cross sections are going to be pentagons. I'm going to write underneath here. All right, so if you take the cross section parallel to the bases, both cross sections will be in the shape of a pentagon. Okay, for the second part of that, we want to talk about what the differences are. Hey, you can almost see that with the red lines that I drew. Hey, if we look at the left-hand figure, no matter where you take that figure and where you slice it, every single slice that you take is going to be congruent. Okay, so as you're moving up that figure, if you want to think about it as a cake, each slice of cake is going to be congruent. They're all going to be exactly the same. However, if you look at the right-hand picture, as you go up, look at my red lines getting smaller and smaller and smaller. As you go up and you take slices of that cake, they're going to get smaller and smaller and smaller. So again, I'll write underneath here. So every cross section of the pyramid that is parallel to the base will get smaller and smaller as you move up the pyramid. But every cross section of the prism is going to be the same size. Every cross section of the pyramid that is parallel to the base will get smaller as you move up the pyramid. Every cross section of the prism will be the same size. Okay, again, this one on the left is the prism. This one is the pyramid. Okay, pyramid always comes to a point. Think about your pyramids in Egypt. Okay, so for 6 and 7, we want to choose the correct net for each solid shape. Again, a net would be, if you cut out those figures and then tried to fold it, which would give you back the cone. Okay, looks like choice A is going to work right away for number 6. If you folded up choice B is going to give you a soup can. It's going to give you a cylinder. That's not a cone. And if you folded C, you're going to end up with a cube. So again, that's not going to give you your cone back here. Okay, and for number 7, if you folded A, you're going to get a pyramid for this one. Okay, and again, it's going to have a square base as its pyramid, as its base there. And it's going to come up to a point. So that's not going to work. Okay, for B, B is if you fold it, and again, you have 2 triangular bases, and then you have one rectangle here, one rectangle there, and then a third one. Let me change colors to get the third one. You have a third rectangle over there, so you need 3 rectangles. This one has 1, 2, 3 rectangles and the 2 triangles, so that one is going to be your answer there. If you fold C, you're going to have a triangular pyramid. So you're going to have a triangle base, and then it's going to come up to a point at the top. Again, this one is not coming up to a tip. Okay, it's not a pyramid. Okay, and that is it for this section.